Good morning, class. Today we are going to start our unit on data networks. As you can see, the components of networking are vast. Networks are comprised both of hardware and software and are pretty much an integral component to our everyday life. We will start this unit on networks talking about why networks have become so important. We will look at the original standards that were put into place to define networks, and then look at sort of the big picture of what we accomplish with networks. After that, I will take you through an introduction to some of the details that allow data to be shared and transported and saved for our use. First, let's take a look at the pillars of information technology. And these are the different aspects of the IT discipline. And as you can see, one of the pillars of the 5 pillars is networking. The component, data networking, is what ties everything together. Without networks, you would not be able to share data and information. You would not be able to move it from one place to another, to use it in a different location and save it in a different location. So in fact, our ability to communicate digitally is totally supported and facilitated by data networks. And while we might imagine, especially since you've been in the networking lab, you might imagine that data networks are not that large. But as you look at this particular picture, you see a couple of networking operations centers, and you can see the vast amount of equipment that it takes to support large-scale data networks. Obviously one is Hollywood, the one on the bottom is one of the Netflix data centers. And so you can see that the supporting of networks takes a great deal of hardware, but it also takes a great deal of software to provide this global network infrastructure that we use without thought every day. So let's start by thinking about what happens when you type www.google.com and hit enter. Well, you know what happens. You get the search engine window, right? That's exactly what happens. And then you put in your query and you hit enter again, and eventually you get an answer back, a list of hits, and you proceed to do or acquire the information that you're interested in. Under that, what you don't know is what's going on behind the scenes between the time you hit the enter key and the time you get the display back with the information you requested. It turns out that not only is there a lot of hardware between you and the destination or the source of your information, but there are also lots of different pieces of software and protocols that it takes to make all of this happen. Some of them, for instance, and this is alphabet soup to you now, but we're going to talk about these different components over the course of the next 3 lectures. There are protocols such as DHCP, which is Domain Host Configuration Protocol. There is DNS, Domain Name Services. There's ARP, Address Resolution Protocol, OSPF, Open Shortest Path First, and many, many others that we will talk about. So let's talk a little bit about standards. Why are standards important? Well, standards are what allow interoperability. If you put standards in place, then anyone who manufactures or develops a product and uses or adheres to the standards can then interoperate with any other manufacturer's product in the same area. So when we look at networking technologies, where we have a lot of what I call moving parts, there are lots of different pieces of hardware, lots of different protocols, different pieces of software. If we adhere to standards, if the developers and the manufacturers adhere to the standards, it means that the product that they developed and put out to market can work with some other company's products, and therefore improves their marketability, but also improves the customer's ability to choose exactly what it is you need to do the job that you want. So standards are important because you, on the client side, get a better choice of what you're going to buy and what you're going to implement. And you have some sense of comfort that these different components will work together if they are compliant with the standards. So let's take a look at one of the early standards. The OSI model is a standard. It is a reference model for how to build a network. We can use it to understand networking and the different functions that have to occur in order for data to successfully make it from sender to receiver. It allows us to compartmentalize network technologies, both hardware and software, by defining functionality and then putting the components in the appropriate functional compartment. And it allows us to aid in the development and interoperability of the hardware and software being utilized. TCP/IP is a different issue altogether. TCP/IP, while it has become, in a sense, a standard and a model, is really an implementation. It is a protocol suite. But we also do reference the TCP/IP model. And it is another way of organizing the functions that are required to transmit data from one place to another. Both of these models account for the same functions, they just organize them a little bit differently. And so I'm going to take you through both models and also then take a look at TCP/IP in terms of its implementation. The Open Systems Interconnection, or OSI model, is the foundation of networking. It is a concept, it is conceptual, in other words, it is documented. It's something that you use when you're getting ready to build a protocol or a piece of equipment that's going to be included in a network. It's open source, and it really helps to organize network technologies. It can help you also to troubleshoot network problems because you have compartmentalized the functions and therefore also the hardware components and software components. It helps you to isolate and identify network problems. The OSI model is a 7-layer model. You can see that in the picture to the right. And each one of these layers has a specific function or role. Now these 7 layers are numbered 1 to 7, starting with the physical layer at 1 up to the application level being number 7. If you're trying to remember the order of the 7 layers, one little mnemonic that I use is all people seem to need data processing. And if you take the first letter of each word in that sentence, it actually then matches to one of the layers, so you can remember the layers in order. Each one of these layers has associated with it protocols, software, and hardware. and therefore, as I said before, they're compartmentalized and easily identified and mapped. This particular model was developed by the International Organization of Standardization, or ISO, back in the 1980s. So let's take a look at what goes on at each one of the layers. At the physical layer, we have what it says, physical components, but some of them are not what you might think. This includes signaling and encoding. In other words, how do I take the representation of zeros and ones inside the computer system and then encode it and transform it into a signal that will go over a copper wire or over a fiber cable. It also specifies the cabling standards, what classification, weight, size of copper, how many wires, how are they, what do they call it, terminated. In other words, what ends do I use on the cabling, etc. So all the hardware specifications, the electrical specifications, the optical specifications if we're using fiber, the connectors that are used, all of that is specified at the physical layer. The data link layer, or layer 2, now provides us with a first level of addressing. We call this physical addressing. It could also be referred to as hardware addressing. And it is associated with the network interface card, which is part of the physical layer, but also part of the data link layer. Data link layer also provides for media access. How do I get access to the media that I'm going to send the data on? So if I'm going on a copper wire and I've got lots of different devices contending for access on that copper wire, whose turn is it? So we have to have a set of rules about how I get access to the media. I also organize data at this layer, and I build what's called a frame, and I also provide for some error detection at layer 2. The network layer provides for logical addressing, and this logical addressing is used to move data from one network to another. It also provides for data encapsulation, and you can think of encapsulation as putting something in an envelope, and we're going to go into that a little bit more later. There's also the ability to fragment and assemble data components or data at this layer. And the reason is that I may have more data to send than I can physically fit in one particular envelope, and so I have to break it up into pieces and put it in different envelopes and then put it all back together again at the receiving end. The transport layer provides what we call process-to-process communication. So just as we talked about, for instance, in Linux, you have processes running on the end nodes, the sender and the receiver. I have to establish a connection between the sender and receiver, and this is called process-to-process communication. Part of that is having an acknowledgement mechanism so that you can account for all of the data that's been transmitted and the ability to recover from errors by using retransmission. We also can segment data at this layer and also reassemble it. The session layer does session management and manages the connection and termination of sessions. The presentation layer provides for things like data translation, encoding, and compression, and also encryption. And encoding is actually that mechanism that says, okay, how am I going to define the letter A in binary? What combination of ones and zeros defines the letter A? What combination of ones and zeros defines a capital A versus a little a? So that's encoding, and there are different codes for that. One of them is called ASCII, and that is the code that is used on personal computers, for instance. And then you get to layer 7, or the application layer, where you get to the user interface. So let's compare the OSI model to the TCP/IP model. On the left, I have the OSI model, the 7 layers of the OSI model as I've discussed. On the right-hand side, you see 4 layers. There are different diagrams of the TCP/IP model. Some have 4, some have 3, and some have 5. So why is this? Why the discrepancy? Well, it depends on whether you want to include, some people won't include the physical layer because it technically isn't part of the TCP/IP protocol suite. It's hardware. And to some degree, the network interface is not part of TCP/IP. Again, it's part of the model, but not part of the protocol. So some people won't look at this as part of the model or one of the layers of the models. And so they will say, well, no, TCP/IP is a 3-layer model because it's really only layers 3, 4, and 5. And you can see that their internet layer maps directly to the network layer in OSI, and the transport layer in TCP/IP maps to transport layer in the OSI model, and then their application layer on the TCP/IP model maps to a combination of the session, presentation, and application layer of the OSI model. So I tend to think of the model, TCP/IP, as a 5-layer model because the whole model includes hardware at the physical layer and the network interface, the internet layer, the transport layer, and application layer. But when I'm talking about the protocol suite really only starts at layer 3 and goes up through layer 7. In other words, the TCP/IP protocols only exist at layers 3 and above. So network devices exist or function at different layers of the models. So if we start with the physical or data link layer, we've got hubs and repeaters at layer 1. We've got bridges and switches at the data link layer or layer 2. We've got routers and gateways at the network layer or layer 3. And then the clients and server devices at transport and application layer. Some devices can in fact function at multiple layers. For instance, there are switches that function both at layer 2 and at layer 3. Okay, so that's an example. We connected also, let's say routers. There are some routers that do have some application function. So you will see some of the devices cross into different layers or multiple layers, but these are the traditional areas in which they function. And we will be talking about each of these in more detail when we get back from spring break. So let's take a look at some of the protocols and specifications that exist at each of the layers. At the physical layer, I can have a specification like an EIA TIA 586A. Well, what is all that about? Well, that's really just a cabling specification for an Ethernet cable. Right? And that defines the physical and electrical specifications for the cable that you're going to use for Ethernet. Then there's Manchester encoding. That again is a physical layer. How do I take the data from inside, which is digital, inside the computer and now convert it into a signal to put out on a wire? And I use Manchester encoding, and I define certain voltages to represent a 0 and certain voltages or changes in voltage to define a 1. Okay, and that's also a physical specification. At the data link layer, we define things like local area network specifications. So, for instance, 802.3, or what many of you will know as Ethernet, is defined at layer 2, and then there's 802.5, which is token ring, which is not used much anymore, and then 802.1 is a switching protocol called trunking, which I think we're going to get to do in lab. At the network layer, you have protocols like IP, Internet Protocol, ICMP, and RIP. RIP is a routing protocol. ICMP is an error messaging system. At layer 4, you have a transport control protocol, or TCP, and UDP, which is a user datagram protocol. At the session layer, there's a SIP protocol, or a session initiation protocol, which is used in streaming media and voice over IP. The presentation layer, remember I mentioned ASCII before, there's an encoding protocol, there's MPEG, GIF, these are all presentation layer protocols. And then you get to the application layer where you have SMTP, which is the Simple Mail Transport Protocol. Then there's the File Transfer Protocol, Domain Name Services, and HTTP, which is the web. The other way to look at this is to look at different data types. So at different layers, we have different data units. Now we call these protocol data units. And so at each layer, I construct a different protocol data unit, and I'm going to show you this in a small animation later on. But for now, just take a look at what happens at each layer in terms of what type of unit, protocol data unit, I create, and what devices operate at which layers. If you look at the left, that represents the sending device, and on the right, we have the receiving device. And so if you're going or transmitting through a hub, hubs only operate with bits. They recognize ones and zeros coming in, and they send out ones and zeros, and that's all they know. But if you go into a switch, switches operate at layer 2, and the unit at layer 2 is called a frame. And they understand the structure of a frame, they understand how to parse a frame, they know what the different fields in that frame are, and they use the physical addresses that are created at the data link layer to make their forwarding decisions. When you get to the router, routers operate, their highest functionality is at layer 3, and they are working with packets. And packets include in them the source and destination IP addresses, which allow you to go from network to network. So routers use that information to forward the information. They use the IP addressing to move data from network to network. At layer 4, we have TCP segments. And at layer 5, there are no specific, the data types are specific to the applications and therefore not included in this diagram. So let's talk about what you need to deliver data across a data network. If you were sending mail through the good old U.S. Postal Service, you would have to do something to allow that letter to be delivered successfully. You would have to put an address on that envelope. That address would include a street address of the destination. It would include, if it was in the U.S., a city and a state and a zip code. And it would include the name of the individual who you were writing to. So let's see how that matches up to delivering data across a network. We have to start with a MAC, or physical address. MAC stands for Media Access Control. And the data link layer uses physical addresses to identify nodes on the network. And this is much like your house address. Every node on a network has to have a unique physical address. And I'll show you shortly how that is accomplished. So there must not be any duplication globally of MAC addresses or physical addresses. The other term, by the way, that gets used that you'll see for this address is sometimes called a hardware address. The reason for that is that this address is actually encoded on the network interface cards and that is done by the manufacturer. So when the network interface cards are embedded or installed into devices, they already have the physical addresses encoded on them. So if you look at your phone, your laptop, your tower PCs, all of those devices, any network connected device has a network interface card, and that network interface card has a physical address that was put on there by the manufacturer. For Ethernet, and that's the networking kind of network we're going to look at, each address is represented by a unique 48-bit address, and we represent it in hexadecimal. So here is a hexadecimal number. Hex is base 16, and base 16 means that I have to have numbers 0 to 15 represented with one digit. And so what we did to represent 10 through 15 is we used letters A through F. So a 10 is equal to an A, and 11 is equal to a B, etc., until you get to F, and F is a 15. Okay, so you can see here that we have 6, C, and so C would be equivalent to a decimal 12. We have F, which is equivalent to a decimal 15. These 12 digits are sort of a shorthand for the 48-bit address, because 4 bits in binary can be converted into one hex number. So if we looked at this number in binary, you would see, for instance, the first 4 bits there are a 6 in hex. The second group of 4 bits is a C, that's equivalent to a 12 in decimal. Then you see an F, which is all ones. All right, the next one is a 0, etc. So each one of those 12 digits is represented by 4 bits. And vice versa, you can take 4 bits and convert it into one hex digit. The MAC address is divided into 2 components. The first is the first 24 bits of the address is a vendor code. That vendor code is called an OUI and is assigned by IEEE, which is the registration authority for MAC addresses on Ethernet cards. Another example of this would be, for instance, if I looked at the first 24 bits and then converted it to hex, DEC is represented by AA0000. And Sun has 082000. And if you go out to IEEE's OUI vendor registry, you can look up any MAC address, OUI, which is the first 24 bits. You can look it up there in numerical order, and you can see who the vendor is. The second 24 bits is a vendor-assigned unique serial number. And this is how we get uniqueness amongst MAC addresses. If I'm a vendor making network cards, in this case Ethernet cards, I would be able to manufacture 2 to the 24th cards, which is a very big number. It is over 16 million. Okay, it's 16,777,000 and a few hundred. So it's a very big, I can manufacture lots of boards. But what if I've used every serial number? Well, then I go back to IEEE and I buy another OUI. Okay, this is there is a fee that the manufacturer pays for the OUI. But this ensures that we have uniqueness amongst all of the network interface cards that are out there. So here's another example, 12 hex digits paired in 2 groups of 2, representing an octet. Okay, so I take 2 hex digits, and that's called an octet because it's 8 bits. It's equivalent to 8 bits. The octets are read left to right, and each octet is read least significant bit to most significant bit. The least significant bit is going to be the right-hand end, and the most significant bit will be the left end. So the address above would be read by looking at the first octet, which is Fox 0, F0, and the system would actually read that as 00001111. It would then move on to the second octet and read backwards, starting from the, if you convert it too easy into binary, and then read it from right to left. in which case I've represented it down below as 0111 0100. Another way to look at that, therefore, is if we look at AA0000 and look at what we would interpret that as 10101010 followed by 16 zeros, it's actually read as 01010101 followed by 16 zeros. There are three general categories of Ethernet MAC addresses. There is a unicast address. This is the unique address that is specific to an interface card. There is one address per network interface card. And this is the way that I can address a specific node or a specific network interface card on a network. And I say it that way purposely because some devices actually have multiple network interface cards in them. So they would have multiple physical addresses because the physical address is associated with the network interface card, not the node itself. So if I have multiple cards, then I have multiple addresses in that device. Okay, one for each card. This is like having a house address. Okay, so you could look at your house address, and if I had two NICs, maybe that's like a duplex, right? So you have two different addresses, but they're both in the same building. A broadcast address is a frame that's sent with a destination of all ones, 48 ones, or in hacks that would be all Fs, and this results in all devices on the local network reading or processing that frame. This is something that we're sending out to everyone. So for instance, if I were to send an email to everyone in the class, if I think of all of the people involved with our class as being my network, and I sent an email to everybody, right, that would be the equivalent of a broadcast. And everybody would be required to read it. Multicast address, however, is a frame sent to a subset of devices on a local area network. And the network interface cards are programmed to receive certain multicast addresses. A multicast MAC address must have a 1 in the first bit, okay, which is actually the least significant bit of the first octet. Okay, a unicast address would have a 0 in the least significant bit of the first octet. And that's the first bit. Remember, that would be the first bit that is read. Now we're going to move up a layer, and we're going to go to layer 3. We've talked about the physical hardware address that is like the street address on your house. Now we have to get you to the right neighborhood. And on your letter, that would be city and state. How do I get your zip code, so to speak? How do I get you to the right neighborhood? And I use IP version 4 addresses to do that. And I say specifically version 4. There's also version 6, and I'm not ignoring that. But version 4 is still the most widely deployed version of IP. And so that is the one that we will focus on for our journey through networking. Just as we represented MAC addresses in binary and hex, IP addresses are represented in binary and decimal. Now, the IP version 4 address is a 32-bit address. It is divided up into 4 octets, and each octet is separated by a decimal point. We call that dotted decimal notation, or decimal quad notation, dotted quad notation. There are a number of different ways, but at the end of the day, you end up with 4 numbers, each separated by a decimal point. Because that is an octet, and that means I have 8 bits, 2 to the 8th equals 256. That means I can make up 256 combinations of 1s and 0s with those 8 bits. So I can represent every number from 0 to 255 in one of those octets. So the smallest number smallest IP address you would ever see would be 0.0.0.0. The largest number would be 255.255.255.255. You will never see a number greater than 255 in any one of those quadrants. Not a valid address anyway. The IP address is divided into two parts. It has a network portion and a host portion. The network portion is distinguished from the host portion through the use of what we call a mask, a subnet mask or a network mask. If you look at the example, we have an IP address of 192.168.100.23, and we have a mask of 255.255.255.1. What the mask does is, every place in the mask that has a 1, the corresponding bit in the IP address is the network portion, is part of the network portion of the address. And the bits in the mask, the 1 bits, have to be contiguous. They have to be next to each other. So you never have any gaps there. It's always all 1s representing the network portion, and then you go to 0s when you're representing the host portion. And so there's a clear delineation. So in this case, because I have 24 1s, the first 24 bits of the IP address, which are the first 3 quadrants, are the network portion of the address. So 192.168.100 is the network portion, 23 is the host portion. If I wanted to represent just the network address, I would put a 0 in the host portion of the address, and so it would say 192.168.100.0, and that would represent the entire network. When I put the host portion in, this is a unicast IP address. In other words, it's specific to that particular node or that particular NIC, network interface card. There are also some special addresses in IP. Along with the fact that you've got unicast, broadcast, and multicast in IP version 4, just like you do in MAC addressing, you also have a loopback address, which is 127.0.0.1, and that's a special address that's used for testing. It does not have to go out on the network. It goes down to the network interface card and then loops back up to the application. So you can test network-based applications without actually being connected to a network. As I mentioned before, there's a network address where you put 0s in the host portion of the address, but you have the network portion of the address in place. That will identify a network or a subnetwork. You have an automatic private IP address, and this is for use with Windows systems only. This is a self-assigned address. It is a special 169.254 address. In other words, we use, for the first 2 octets, we use 169.254, and then the system, if it cannot get an address for some reason, an IP address for some reason, it will select the host portion of the address, test to make sure nobody else is using it, and as long as no one else is using it, it will assign it to itself. If someone else is using it, he will then pick another address in that address range. Because there are 16 bits available for the host portion, we have 2 to the 16th available addresses, which is a very large number. It's 65,536 different addresses, so there are plenty of choices there. We also have private addresses. These are addresses that do not go out on the global internet without translation to what's called a globally acceptable address. And this allows, this was put in place to address the IP version 4 address depletion problem, which we'll discuss in another class. But there are 3 different networks that are used for private addressing. There's the 10.0.0.0 network, there's the 172.16.0.0 network, and the 192.168.0.0 network. In addition, as I mentioned, I showed you what a unicast address looked like. That is the IP address that has both a network and a host portion. There is broadcast, and in IP, it is all 1s, just like it is in the MAC address. The only difference is that when it gets translated to decimal, and it looks at like 255.255.255.255. That is a broadcast at layer 3. There is also multicast addressing, which again is also a group address, but a layer 3 group address. So what happens if you want to look up this information? Well, on a Windows machine, you would go into what we call the command window, and you could issue a command called ipconfig /all, and you would get a screen like the one that's shown here. And if you look down through that, you will see one item labeled physical address, so it tells you what the MAC address is on this particular wireless node. It also shows you, if you look a little bit further, what the IP version 4 address is, the subnet mask, along with a bunch of other information such as the DHCP server, DNS servers, etc. So there's a lot of information here, and we will sort of walk through this as we're doing lab, and you'll see and learn what most of this means before we are done. So let's talk about data delivery. We've now seen how IP addressing can get the frame to the right network because it has a network portion of the address. The router can distinguish that. It can separate the network portion from the host portion and then make a routing decision and send it to the right network. We can get it, once we're at the right network, we can get it to the right node using the MAC addressing in the frame at layer 2. But once the frame has arrived at the destination host, how does that data get delivered to the appropriate process? In other words, how do I get the letter to the right person inside the house? I've gotten it to the city and state and the street address, and now it's at the house, and I have to deliver it to an individual in the house. The way we do that in networking is that we use the transport layer, or layer 4. And what we use in layer 4 are port addresses. These there are a 16-bit identifier field in both UDP and TCP headers, and that allows for 65,536 different ports. There are 3 different types of ports for each protocol. So in other words, I have one set for UDP, another identically numbered set for TCP. And the 3 categories are what we called well-known ports, which is 0 to 1023. These are assigned. There is an organization that is part of the Internet Society called IANA, I-A-N-A, the Internet Assigned Numbers Authority, and they manage these ports. They basically restrict these for sort of global types of application usage. So, for instance, web servers have a port in this range, which is port 80. FTP has 2 ports in this range, 20 and 21. So these are generalized applications that have a global nature or wide usage. They would have well-known ports. These are typically, though not 100%, these are typically server applications or server ports. They identify servers. There are also registered ports. The registered ports can range from 1024 to 49152, and these are for other applications that have been developed and need to be defined. This is sort of a gentleman's agreement. IANA keeps a registry. If you had an application that you wanted to put up and that needed a port, you would look in their registry, see what port is not being used, and then you would go to IANA and register it with them, and they would document that in the registry so no one else uses it. And then there's the dynamic port range, 49,000 to 153 to 65,535, and these ports are the ones that the clients use. When I start a conversation as a client, I select a port from the dynamic range. In other words, I have all these ports sitting in a pool on my system, and I pick the next available one and use it for my communications going out. And the reason is that in a client-server environment, which is the way networks work today and applications work, the client always initiates the conversation. So since the client initiates it, they start by selecting a dynamic port, and since they're going to a server, they know the well-known port, or if it's a registered port, then they have been told what that port is that they're to use. And this is what gets us directly to an application, because these ports are associated with applications. So when I get to the server end, that port will point to the application. I might be running several on my machine at the same time. So maybe I have DNS running, and I've got FTP running, and I've got web browsers open. I may have multiple web browsers open, but I have the ability to get to them through the port numbers. And when I return to the client the answer, so let's say I go to a web server to get some information, when he returns it to me, he has my dynamic port number because I've put that in the UDP or TCP header, and he returns it to me using that port number, and I know which session and which application that data goes to. So now let's look at the concept of encapsulation. If you look at the top, we have a message that we're going to send, and that's the application layer, and that message is going to be sent down and, let's say, packed into or put into a UDP envelope. And by that I mean I put it in an envelope and I'm going to label it with a UDP header. So I'm going to add some bits of data, 8 bytes to be specific, in front of the data. And I'm going to put those together and I'm going to send that down to IP. IP looks at that whole unified package, the UDP header and data, as data, and it adds its own header or IP header, and its header is 20 bytes, so it adds that onto the front end. It then sends it down to layer 2, and if we're on an Ethernet network, Ethernet then puts a frame around it or another envelope, and we've got a header, frame header, and then we have what we call a footer or a trailer. I actually put something on the end which is used for error detection. So you might think of this encapsulation as a set of nested Russian dolls. So let's take a look at what this looks like. I have something that I'm sending from a device A, and I send the data down to application data. It's going to put its application header on it. I will then send that down to the transport layer, and this, because it's FTP, it uses TCP at layer 4. I add the TCP header onto it. I will then send it down to the network layer or internetwork layer and put the IP header on it. Again, encapsulating. I'm putting it in a different envelope as I work my way down. I'm putting it in a new envelope each time I go down a layer. I get to layer 2 and I put the 802.3 or Ethernet header on the front end, and I put the CRC or the error cyclic redundancy check or error detection code on the trailing end. This then has to get converted and encoded to be put out on the physical media. So now we're at the receiving end, and the data comes across the network, and I'm going to now de-encapsulate. I'm going to send it up the protocol stack, and when I de-encapsulate, what I'm doing is using information in the header to determine where to send the data next until I get all the way back up to the destination device. So the bits have come in. I recognize at layer 2 a frame format. I look at the frame header, which is 802.3, and I look at the trailer or the CRC. I'm going to check the CRC to make sure the data has not been corrupted, and once that's done, I'm going to take the trailer off, and then I'm going to look at the 802.3 header and look at what protocol do I have to send this data to next. And in that header, it tells me send this to IP. So I take the header off and I send the data up to layer 3. When I get up to layer 3, I will look in the IP header and remove that after I determine that this has to be sent up to TCP. Once I take it up to TCP, TCP is going to look at the port address, and that port address is going to say, oh, this is an FTP. This goes to the FTP application. It's going to strip off the header. He's going to send it up to FTP, and FTP is going to strip off its header and deliver the data to the final device. And that is de-encapsulation. Another way to look at encapsulation is to look at a frame that has been transmitted and captured in a tool called Wireshark. And in this tool you can see the layer 2 or Ethernet layer, the data link layer, and you will see there that you've got the source and destination MAC addresses. What it has done, it looks a little strange, is it has actually converted the OUI into the company name. So you're only seeing the last 24 bits because the first 24 bits have been converted into the company that manufactured the network interface card. So you have the source and the destination. At layer 3, you have IP, and you see the source and destination IP address. And then at layer 4, you have UDP, and you see the source and destination port addresses. After that, you go down to DNS, which is the domain name service or system, and that's the application code. So you can see the destination port, if you look at layer 4, is 53. And 53 is the port number for DNS. So what is Wireshark? Well, Wireshark is a free network analyzer or packet sniffing tool. You use it to capture and display your network traffic, and it converts it into a user-readable form. And you do this, you can learn how protocols work, but you can also troubleshoot your network using this information. You capture the information in real time, you can save it and analyze it later. It is a tool that has to be used responsibly because you can't just go around sniffing traffic anywheres. You can use it freely in our labs, but I would not use it outside of the lab to sniff traffic at all. So now we get back to our original question. Do you know what happens when you type www.google.com and hit enter? Well, when we started, we know that we got the search screen. But now you know that it takes hardware and software and protocols to make all of that happen under the hood. So when we have our first lecture after the break, we will take a look at how this really works under the hood from end to end. So at this time, we're at the end of our lecture for today, and I look forward to seeing you on Monday, March 19th.